Hi guys, I'm going to do a quick video on motion in 1D and I'm going to call it part 1 because there will be another video on vertical motion. Okay, so under this I'm going to go quickly. If you want to pause the video and check, you can do that. So we discussed the definition of velocity yesterday. Since this is a calculus based class, I am going to write it as dx by dt. And we also discussed that as v equals to delta x change in displacement over change in time. And when you expand that, you get x final minus x initial divided by t final minus t initial. Usually, we take the t initial equals to 0 and we get x final minus x initial divided by t. Instead of t final minus t initial, we simply get this as t, where t is the elapsed time. Now, similarly, we got the equation for acceleration, actually a definition for the acceleration, and we called it dv by dt. And as discussed before, the intro level, we can write it as dv over dt. And dv, if you expand, that was going to be v final minus v initial over t final minus t initial. And t final minus t initial, once again we can take the initial time to be 0. Then you get v final minus v initial over time. Now, I know that we haven't discussed the vector chapter yet, but the velocity and displacement are vectors. That is why you see these arrows on top of each of these symbols. Now, the next most important thing that I discussed yesterday was the graphing. Now, the graphing was done once for the x versus time, displacement versus time, and the other one was for velocity versus time. Now I did 3 different graphs for x versus time, displacement versus time. So I'm going to quickly draw them here because your quiz is going to be based on this. So when you do the axis, make sure that you mark the units along with that. And the first one that I draw here is the velocity versus x versus time graph with a constant velocity. Now we discussed this graph as the constant velocity graph because the slope which represents the velocity is a constant here. The slope of this graph, which is delta x rise over run, and this is nothing but velocity, right? So throughout this motion, you can see the slope stays a constant. All these points, if you want to draw a line of tangent line, you will see that they all represent the same slope. Now the next graph that I discussed was for changing velocities, and the changing velocity can happen in 2 ways. One is increasing velocity, the other one is decreasing velocity. So here we go with the decreasing velocity first, and I'm going to use the same yellow color, and here we have a decreasing velocity. Now in order to explain this, I used a couple of different points. Point A, you can call this point B, and at the top point C. And then I drew tangents. I'm not going to use the use all the information here, but you can see the tangent lines that I am drawing in each place to find the slope. So you can actually make the right triangle in each case and then find the slope using the rise over run information. But at this point, if you call this point A, point B, and point C, you can see the point C, the slope equals to 0, and the slope represents the velocity. Velocity equals to 0. Velocity is 0, meaning the object that is moving over this time period, let's say this time period, and at the final time, let's call it TF, and at that point the object is stopping. So this is a graph that represents the decreasing velocity. Decreasing velocity. And then the third graph that I introduced to you was for increasing velocity. And at this point, I believe that you all can decide what the shape of this third graph is. And there you have. I'm going to draw this flat at the beginning, and then you can see that the slope is increasing. So you can pick one point at the beginning, another point and another point, and you can draw the tangent lines just like that. And if you want to draw the the right triangles to find the slopes, you can go ahead and do that. So you can call this as A, B and C like that earlier, just like what we did at the previous case. And you can see the slope at this point, at point A, equals to 0. And then the slope means the velocity in x versus time graphs. So you can say the velocity equals to 0. Now, unlike in the last time, at this point you cannot say that the object is stopping, because the time at this point is t equals to 0. So you can instead say that the object is starting with an initial velocity of 0. So at this point, initial velocity equals to 0. Earlier you can see that the final velocity, I'm using my red pen here to circle the previous graph, circle the TF on the previous graph, TF, and there you can see the corresponding point is C, and down here I am using again the red pen to circle the t equals to 0. T equals to 0 means the initial point, and at the initial point you have a flat curve here, flat slope here, and that represents the velocity equals to 0, just like in the previous case, yes. But instead of calling the final velocity equals to 0, here we call it initial velocity equals to 0. In fact, here if you like to call this as final velocity, that's also fine. You can say final velocity equals to 0. So these are the three graphs that you want to know. Moving forward, we can always ask to plot a graph for displacement versus time, and increasing velocity, decreasing velocity, and constant velocities. Now if I for example, if I draw something like this, let's say example, and there I have x-axis and the y-axis. X-axis meaning the x displacement axis, and the time axis, not the y-axis, time axis over there. And if I give you a plot like this, let me erase the axis over here and extend that a little bit like that. So you should be able to explain the nature of this graph. So I can call this T1, initial velocity. I can call this T2, a middle velocity, and here you have T3. So I can ask you to explain the behavior going from T1 to T2, and then from T2 to T3. And we discussed velocity is a vector, therefore it can have both positive and negative velocities, right? So I'm not going to give you the answer here, but I'm going to give you a little bit of help. If I were you, I would actually draw these points A, B and C, and D and E as well. And I'm gonna draw these tangent lines, and I'm going to discuss the velocities. And you can see going forward at point A, point B, you see a positive slope. And also you can see the slope is decreasing. And going from DE, like from C to D and D to E, you can see the slope is increasing, but it is pointed in a negative direction. So you should be able to explain a graph like this. And then the second thing that we discussed was velocity. Velocity versus time graph. Okay, let me show you one example. In this class, mainly we are looking at constant velocities. So velocity versus time graph. And now our y-axis is velocity, x-axis stays as time. Just like last time, we are going to draw a constant line, like a linear behavior of velocity as a function of time. And then we mark a couple of points. And then we can find the slope of this line. Again, you can see the slope is a constant here. And the rise is delta V, because the y-axis here is velocity, and meter per second is the unit. And if you take this to be V final, that is V initial, then this goes as delta V. And then the same over here, T initial, T final, and this goes as delta T. So when the slope equals to delta V over delta T, that tells us the slope of velocity versus time graph is nothing but the acceleration. So here we have a positive acceleration given by this yellow line. Now if you want to go further, I don't think I discussed this in the class. Go ahead and draw increasing accelerations, decreasing accelerations, right? Those type of things are still possible. But as I said, we are not going to look at varying accelerations in this class. Not as much, I would say. Yeah. So here you have a slope like that, and there you have a slope like that. And you can see the slope is increasing, going up. As a result, you can say the acceleration also is increasing. Now the last one is acceleration versus time graphs. As I said, we are mainly dealing with positive and negative accelerations that are constants. So you will have, just let me give you one example, acceleration versus time graph. And I am going to draw this for positive and negative acceleration. So let's say that here you have meter per second square is the unit of acceleration. Let's say you have a positive constant acceleration. This is a constant, right? Constant acceleration going from t equals 0 to t equals t1. And then after that, it has a negative acceleration, let's say. And then from here to here, a constant negative acceleration. And this is how you draw that. So a positive acceleration, let's say that this is 3 meter per second square. And the scale over here is 3. And let's say this is a negative 5, because I did not draw it symmetrically. And this line represents a constant negative 5 meter per second square acceleration. Okay, so that is how you draw the acceleration versus time graphs for a given motion. Now now that we have some idea about what is happening over here, for example, we should be able to discuss graphs like this. Example number 2 here. So let's say x x versus time. Okay, don't forget to check the axis. This is x. And then the x can change like this. From t equals to 0, t equals to, let's say, 1 second. You can have a constant velocity, positive velocity. And then from t equals to 2 seconds, nothing happening, nothing's going to happen, and the displacement stays a constant. And then after 2 seconds, it's coming in the opposite direction or going in the opposite direction. So this is more or less like 2.5 seconds. So at 2.5 seconds, it has a different type of a motion. In other words, the slope is actually different, but the velocity stays a constant. So remember, x versus time graphs, the slope always gives you the velocity. So here you have a flat line, meaning flat slope. Therefore, there is no motion or zero velocity. And here you have a negative slope that represents a negative acceleration. Negative velocity. Okay, guys. Now I am going to briefly give you the 3 equations, the kinematic equations that we discussed in the class. So here we go. Kinematic equations. So I'm going to write down the most important ones. V final equals V initial. The arrows are for to represent that they are vectors. And the second one, delta x equals V initial t plus 1/2 a t square. And then the third one, V final square equals V initial square plus 2a delta x. So these are the 3 equations that we were looking at yesterday. Now, in all these cases, you can see in all 3 equations, you can see a, the acceleration a is constant. In all these cases, xa is constant. If a is not constant, if a is not a constant, then I'm going to show you how the first equation changes. The first equation changes, and we will have to write an integration, and we will have to do the integration, and t equals whatever the initial time is, and it goes from initial time to a final time. So just to give you a quick example of AT, because you guys have taken calculus, if AT is like, let's say 3t plus 5 or something, and if t is changing from 0 to 2 seconds, then this integration going from 0 to 2 seconds and at, so I'm going to substitute a here, 3t plus 5 dt, and that's going to be equal to 3t square over 2 plus 5t. Since this is a definite integral, you don't have to put the constant. Now you are applying the limits. So there you will have 3 divided by 2. Upper limit is 2. So you will have 2 square and plus 5 times 2. And then when you substitute 0 in both places, you will end up with a 0. So this is going to be the final answer, and you will have to use that acceleration in the equation and find the V final. So here you will have, I believe you get 16. 4 and 2 times 3 times 2 is 6, and 5 times 2 is 10, and 16. Yeah, so you will have to substitute for this term 16 meter per second square and conclude the work. So the video is getting little longer, guys. I am going to stop it here. and I plan to do these type of videos every week. All right, see you later. Bye.